Good morning to everyone. This is Dr. Polaiah, working as a professor in the Department of IT, Institution of Aeronautical Engineering, Hyderabad. I'm very happy to share my today thought, that is delivering a video lecture on wavelets and multi-resolution processing. I'll repeat. Today my topic is wavelets and multi-resolution processing. It is the topic which going to be covered from the image processing syllabus from unit number 4. So where we are in the unit number 4, that is model number 4, which we are in a continuation of discussion of one topic by another, which help us for the sake of understanding that complete module in terms of topic by topic. Okay, so under this, this is one of the topic. Coming to the we have to understand what does it mean wavelets and multi-resolution processing. Yes, we are all aware about multi-wavelet uh, transform is used to analyze a signal, that is image. Signal is here, image, because we are under the image processing. So into different frequency components at a different resolution scales that we called multi-resolution. Different resolution scale is nothing but your multi-resolution. Understand? So I'll repeat once again. What does it mean wavelet transform? It is used to analyze a image into different frequency components at different resolution scales. We call as a multi-resolution. This allows revealing images spatial and frequency attributes simultaneously. In addition, features that might go undetected at one resolution may be easy to spot at another. So wavelet and multi-resolution processing is right now we are going to concentrate as we from the previous class. There we are discussing a simple image compression block diagram, which in terms of understanding one block by another, how it is function as a one of the functional block which we have defined just now, wavelets. So what does it mean wavelet or wavelet transform? So that we are, as per definition, we are keeping into understandable from one function to the another function is in simultaneously process. How it is in the sense, by understanding this block diagram, we can go ahead one by another expression. So we are right now here. What does it mean wavelet transform? So wavelet transform, which I said here, the in terms of multi-resolution processing, by taking input noise as input to this and process in terms of multi-resolution processing and goes to keeping into the estimate threshold value that we are going to be keeping into the based on the software tool or hardware threshold value and convert it into the inverse wavelet transform, then we'll get the your denoised image. That is, we are obviously going to concentrate on, by using this wavelet transform, we are going to be find out not only concentrating on removing the noise, but how much noise it is there in the image that can be separated. So we can continue understandable that wavelet, how we are keeping into the multi-resolution processing as multi-resolution expressions, that is called multi-resolution expansions, which we can say multi-resolution analysis, which we can say multi-resolution analysis. This is continue. So that is multi-resolution analysis, representation of a signal. Here signal is nothing but image. It is here signal is nothing but image. That is, an image is in more than one resolution are called more than one scale, which we are process in terms of multi-resolution analysis. So multi-resolution analysis refers to break up into the break up your signal into components, and then which produce the original signal exactly when added back together. To be useful for data analysis, how the signal is decomposed is important here. So multi-resolution expansion, which we can say as in terms of analysis we are taking that in terms of usage of your wavelet transform towards to analyze a image into different frequency component at a different resolution scales is also considered under the part of multi-resolution expansions. Multi-resolution expansions. So this allows revealing images in terms of spatial and frequency attributes simultaneously. In addition, that features that might go undetected at one resolution may be easy to spot at another. Wavelet transform in one dimension, which we concentrate in contrary returns an array one dimension larger than the input data for a one dimensional data, which we obtain an image of the time frequency plane. So we can easily see that the signal nothing but image signal frequencies evolution during the duration of the signal and compare the spectrum with other signal spectra. So that is also very important here. So let us we see that how it can be understandable when we are concentrating wavelet transform in terms of 1D. Wavelet transform in terms of 1D. How it is concentration. Let you take the input, your signal, nothing but image is here, image that we are going to keep into the components that L of n that is called H of n into L of n. Those level 2 coefficients we are going to be divided into two categories. One is your level 3 coefficients and level 3 approximation. So I is nothing but what we call this level of n is the another approximation value. Okay, you can see this scale value which we are keeping on y-axis and versus x-axis. This one-dimensional discrete wavelet which we are going to be keeping on to understand the filter bank representation as A part and the resolution frequency is the B part. So the frequency which we are keeping in terms of in terms of your value which is your divided into image signal, the value which is your divided into image signals. Okay, so you can understand from this level 3 as a low I, level 2 as a frequency, level 1 is a high frequency is also changes. So you can understand here from this one dimensional we expanded here one of the diagram which we called as a block diagram. Block diagram. The block diagram of wavelet transform. So what is this here understanding? The A part is the frequency domain. The B part is which is your analyze in terms of graphical representation. A signal is nothing but here image. Okay, so that image we are divided into two parts. Why? Because depends upon this image frequency values, frequency range we call as a frequency range. If it is lower range of frequency, it allows here through low pass. If it is higher range, then it is allows the high pass filter. Then we'll get the your representation of the graphical representation. Graphical representation. Okay. So wavelet packets, we say that the signal which we are keeping in terms of packet, that's the data. So signal is nothing but here an image which keeping in terms of data compression application that encodes the original image with a few bits. The aim of this image compression is to reduce the frequency of image and store or transform the data in an effective format. It is also reduce the time required for images to be processed in specific system. The wavelet packet method is generalization of wavelet decomposition that offers a richer signal analysis. Wavelet packet atoms are waveforms indexed by three naturally interpreted parameters. Number one, position. Number two, scale. The scale is nothing but here wavelet decomposition, and number three will be frequency component parameters. So these are the three parameters which we are concentrating on the wavelet packet. That wavelet packets which we are continuation is here. Wavelet packets are now we are defined in terms of generalized approach of wavelet decomposition, which introduce the spacious area of possibility of signal analysis that is permits the better accordance analysis to the signal, where the signal is nothing but here we call as image. We call as the image. It transforms the signal to the frequency domain level. So that is the wavelet packet. What we call this one? Wavelet packet. Wavelet packet. Wavelet packet divides the low and high frequency subbanded value. That is, we says that here. That is, we says here. Wavelet analyzing the signal is divided into an approximation and a detailed coefficient value. So wavelet packets nothing but that we can concentrate. An approximation is also divided into text, divided into next level approximation and detail, and continue this technique until they reach a particular level. But in the wavelet packets also concentrate analysis. This process is also achieved on the detail. So, wavelet packet is a part of the wavelet transformation. That is, the low pass filter and high pass filter output repeated to offer a maximum flexible and complex analysis. In this, we understand in composition process in terms of n level may give n plus 1 methods for signal decomposition. So, try to understand here your signal is nothing but image. Your signal is nothing but an image. So, an image which is we are keeping here in continuation of understanding packets, Wn of x is the wavelet packet which n is varies in terms of 0 to n value. That is, we consider here 4 values, that 0, 1, 2, 3, 4, and those values we are going to be repeated here based on the 0 to 1. So, how we this 0 to 1 varying in the sense n minus 1. So, that is n value will vary 0 to capital N minus 1, where n is the it is vary 0, 1, 2, 3, so on. So, that is what we can understand, so on in terms of k. So, we can extend this in terms of additional approximation value, that is W2n plus 1 of x. This is, we can write like this, W2n of n plus 1 of x, which helps us here one of the system of the signal which represent k of h of k, here g of k. So, what do you want to understand in between these two, h of n and g of n? Those are identical to the wavelet, and we find your approximated function phi of x in terms of 1D, in terms of 1D scaling function, and we'll get that phi of x is right now in terms of wavelet transformation. So wavelet function is nothing but we'll expect your you will expect in terms of your WP. What do you mean WP? It is wavelet packet. Wavelet packet. Okay. So wavelet packets, which we are understanding here, ability to further degrade the area of wavelets as follows. That we represent V0 is nothing but your convolution value of E1 of convolution, that is product W1, and which varies in terms of varies. So that product value gives your single packet. In terms of V0 is the signal space, V1 and W1 are approximation and detailed V0 respectively. So this expression is are the subspaces of V0. What is V0? V0 is a signal space. So where it varies, this values of n is here in terms of decomposition series. So the wavelet pocket decomposition of tree for n equal to 2 is as shown in the coming figure. So what do you want to understand that wavelet pocket decomposition of a signal results in considerable redundancy and an increase in the number of wavelet bases, in which the size of the library will grow rapidly when the number of scale levels is increased. Redundancy results in a substantial increase of both computational and storage costs. A funding algorithm is needed for selecting a subset of nodes for signal representation considered suitable for a given application and reducing the computational cost. So that means these nodes should provide a sufficient accurate approximation to give a signal, that is image. The especially by taking the Shannon entropy function measuring the signal economy. So where this entropy value help us in terms of quality. Entropy value will help us quality of the signal. So that Shannon of the entropy cost we are going to be find out in terms of taking one of the mathematical formula which help us as an algorithm that too an efficient algorithm for finding minimal entropy solution in easily uh, contracted. For each node of analysis 3, beginning with the root and proceeding level by level to the leaves. So compute both the entropy of the nodes denoted in terms of E suffix of P. P is nothing but the parent entropy value and entropy of its four offspring denoted EA, EH, EV and ED. These are all the four values. So that four values which are varying in terms of two-dimensional wavelet packets decomposition. So the parent is a two-dimensional array of approximation or in detail coefficients. The offsprings are the filtered approximation, horizontal, vertical, and diagonal details. So the in the merged entropy of a spring is less than the entropy of the parent, that is EA plus EH, EV, ED, or the values which are less than parent entropy value, including the offspring in the analysis tree. If the combined entropy of the offspring is greater than or equal to that of pruning the father of offspring keeping, only the parent is the leaf of the optimal analysis tree. So you can write this as one of the step 2 in another form of the clarity. So if there is a no leaf node, we consider as a C1 is the cost value for the node, and the value C2 is the sum of the cost values of children of that node which we are connecting in terms of entropy. We call as entropy. Entropy, how we represent entropy? E suffix P. So we understand that C1 and C2 values, how we are comparing is if C1 is less than or equal to C2, then we mark the node as part of the best basis group and cancel any marks in the nodes in the subtree of the current node. We can understand that if C1 is greater than C2, then the cost value of the node is replacing the C2. So how we can understand this table here is we compare one to other, the structure of the two-level decomposition of wavelet packets, which we are comparing one to other. That is, we are comparing here high pass to low pass to high pass. That values of decompositions which we are compared to calculate the wavelet packets values. So let us we take one packet data which is in terms of a signal that representation as an image. That representation as an image. What we call that is images. So the images are we consider as a fingerprint and it iris. So iris values and fingerprint. Let it take. So in this example, what we can understand, we find out the noise is there or not. And if noise is there, we wanted to keep it into the denoised value. So separate it. And we make the wavelet transformation towards to your required decomposition. And we going to get check these images with wavelet transform, whether it is prepared perfect detailed data expected or not. We are going to be calculate that one. We are going to be determine that one by the help of your entropy value. So how we may proceed that wavelet with the help of image which consider is fingerprint image. Okay, let you take the input image. Okay, your x-axis and y-axis, and this value is one dimensional. We are keeping as one dimensional. So because we can keep any number of them, but 2D or 3D also possible. But we take here that wavelet transform is finding the perfect entropy based value. So wavelet packets which we are keeping for the iris image also is same which we are discussing. We are in terms of fingerprint, we will also expect here this is an input image and we'll get the resultant image by using the wavelet packets, that is wavelet transformation. Keep in your understanding that the full color image processing is also will going to be processed by the help of by the usage of our wavelet packets. So from the image we convert your required image. Let us take this one is input image. So it is here continuation, and we'll get your output image in terms of result. This resultant is right now we called as a wavelet packet. Nothing but you are finding the entropy value from the parent. Parent is here. So with this, our discussion will going to be end right now by the understanding of the list of references also, which help us for understanding this complete our discussion by the referring textbook 1 and textbook 2. So whenever you are free, please kindly go ahead using of this textbook knowledge also for the sake of understanding our topic. I'm really very thankful for you all patient listening, and we are going to continue with other topics also as per our syllabus. So I'm very thankful once again to each and everyone. Thank you so much.
Like, share, and subscribe. Hit the bell icon for more updates.